All right, now let's talk about multiplication of complex numbers. If a plus bi and c plus di are two complex numbers written in standard form, their products are defined as follows. The product a plus bi times the quantity c plus di is equal to ac plus adi plus bci plus bdi squared, which turns into the quantity a times c minus b times d plus the quantity a times d plus b times c times I. Now, do we need to memorize this formula? Absolutely not, okay? Don't even bother writing it down. All this is saying is that we have to use the distributive property of multiplication. All right? All the exact same rules that you have learned in algebra over the years are still applicable to imaginary numbers. So here we have 3 times the quantity 2 plus 4i. Well, again, we use the distributive property of multiplication. I'm going to take 3 and multiply it by every term in the parentheses. 3 times 2 gives me 6, and 3 times 4i will give me plus 12i. 6 plus 12i. Not too bad. Let's try another one. 5i times negative 1 plus 7i. Again, all I need to do is use the distributive property of multiplication. 5i times negative 1, that gives me a minus 5i. 5i times positive 7i gives me positive 35i squared. Now, this needs to be simplified still. Anytime you have powers of I that are greater than 1, we can reduce it. Recall that I squared is equal to negative 1, so this is 35 times negative 1, which is a negative 35i. My final answer is going to be negative 35 minus 5i. Notice, again, when we're writing answers in standard form, the real component of the complex number always comes first. That is the reason why I brought this minus 35 to the front. And here we have two binomial complex numbers. All right. Again, use the distributive property of multiplication. In this case, we are going to need to FOIL. Take every term in the first parentheses and multiply it by every term in the next parentheses. If I take my first terms, 6 times 2 gives me 12. My outer terms give me a negative 18i. My inner terms give me a minus 4i when I multiply them, and a negative 2i times a negative 3i from my last terms gives me a positive 6i squared. Now we can begin to simplify. Well, combining like terms, negative 18i minus 4i would give me negative 22i. Recall that I squared is equal to negative 1. This is 6 times negative 1, which gives me a negative 6, which I can combine with my first term, 12. 12 minus 6 gives me 6. My final answer here will be 6 minus 22i. All right, let's try another one here. Root 14 plus root 10i times root 14 minus root 10i. Well, again, we need to use the distributive property of multiplication. Root 14 times root 14, that gives me 14. Root 14 times a negative root 10i, that gives me a negative root 140i. Positive root 10i times positive root 14 gives me positive root 140i. And a positive root 10i times a negative root 10i gives me a negative 10i squared. Notice in this particular case that the products of the outer and inner terms are going to add to 0. Those terms cancel out. I have 14 minus a negative 10i squared. I squared is negative 1, so this becomes a 14 plus 10. 14 plus 10 gives us 24 for our final answer. So again, a bunch of products that we were just able to complete. Did we have to memorize this fancy formula? Absolutely not. Just use the algebra that you know already. The same rules of algebra still apply. Now let's take a look at this last product that we just completed. Take a look at these two groupings in parentheses. Notice that they are very similar. However, the signs in between the real and imaginary parts are opposite in each grouping. And notice that when we multiplied those together, we ended up with a real number. This is an important concept, all right? And these are known as complex conjugates. The complex conjugate of a plus bi is a minus bi. Notice again that the signs in between the real parts and imaginary are going to be opposite each other, okay? So anytime we have two complex numbers where the signs are opposite in between the real and imaginary parts, they are going to be complex conjugates. And anytime you multiply complex conjugates, you will always get a real number. A plus bi times the quantity a minus bi is always the real number a squared plus b squared. Now, let's see where that comes from. A plus bi, the quantity a plus bi times the quantity a minus bi. Again, we have to use the distributive property of multiplication. My first terms give me a squared. My outer terms give me a minus abi. My inner terms multiply to give me a plus abi. And my last terms multiply to give me a negative b squared I squared. Well, the outer and inner terms, they're opposites. They add to 0. I have a negative b squared I squared. I squared is the same thing as negative 1, which turns this into a plus b squared. A squared plus b squared. So there's a little shortcut, all right, to recognize if you are multiplying complex conjugates, it's always going to turn into a real number, a squared plus b squared, where a and b, a is the real component of your complex number, and b is the constant multiple in front of your imaginary component. All right. Or instead of memorizing, it doesn't take too much effort to just FOIL everything out. So let's do a little bit of practice. Again, here I am multiplying two complex conjugates. These are complex conjugates because the sign in between the real and imaginary parts of our two complex numbers are opposite each other. Okay, again, I just flip-flop the sign. And the product of complex conjugates is always going to be a real number. So let's multiply them out. Again, use the distributive property of multiplication. I take my first terms. 2 times 2 gives me 4. My outer terms gives me a minus 6i. My inner terms give me a plus 6i. And my last terms give me a minus 9i squared. Again, the outer and inner terms, the products of the outer and inner terms are going to give us 0 there. They cancel out. 4 minus 9i squared. I squared is negative 1, so this minus 9i squared becomes a plus 9. And we end up with 4 plus 9, which is 13. Again, really important to recognize is that multiplying complex conjugates always turns into a real number. This is going to help us with dividing by complex numbers coming right up. So let's talk a little bit about division now. The quotient a plus bi divided by e is equal to a over e plus b divided by e times I. This is saying that if I take a complex number and divide it by a real number, all I have to use is the distributive property of division. And you guys already know the distributive property of division. It says I take every single term in my numerator and I can divide it by my denominator. A divided by e plus b divided by e times I. For example, 7 minus 10i over 2. I could divide each term in the numerator by 2. 7 over 2 minus 10 over 2 times I. 10 over 2 reduces into 5. This is 7 halves minus 5i. All right, not too bad dividing by a real number. What about when we divide a complex number by a pure imaginary number? Pure imaginary means I just have an imaginary component. To do this, we are going to multiply our fraction by I over I. This is how we divide by a pure imaginary. And if you're trying to think about why we do this, having an I in the denominator is something that we want to simplify, right? Remember our definition of I is I equals the square root of negative 1. And so we want to rationalize denominators. In other words, we don't want to leave radicals in denominators of fractions. So we would have to rationalize it by multiplying by the square root of negative 1, right? That's how we rationalize it. Well, that's the same thing as multiplying by I. And the reason I have to do that to the numerator and the denominator is because In doing so, I'm not changing the value of our expression. I'm actually multiplying by 1. Now, again, we have all these complicated formulas here. Do we need to memorize them? No, just do the algebra that you know already. So I have 6 plus 3i divided by the pure imaginary I. When I'm dividing by a pure imaginary, I'm just going to multiply the numerator and the denominator by I. The same thing as multiplying by 1. This process is just rationalizing our denominator, getting rid of the radical in the denominator. Well, multiplying two fractions, I multiply numerators times numerators, denominators times denominators. Distributing gives me 6i plus 3i squared divided by I squared. And now we can simplify our powers of I. Notice 3i squared, that's going to be a negative 3 plus a 6i in the numerator divided by negative 1 in the denominator. Now that we are dividing by a real number, we can use the distributive property of division and divide each one of our terms in the numerator by negative 1, leaving us with 3 minus 6i as our final answer. All right, and finally, when dividing a complex number, a plus bi, by a complex number, c plus di, in order to rationalize our denominator, we must multiply the numerator and the denominator by c minus di over c minus di. Notice that c minus di is the complex conjugate of the denominator. So why do we want to multiply the top and bottom by the complex conjugate of the denominator? Well, recognize that when we multiply by complex conjugates, we are going to end up with a real number. All right, that will get that imaginary number out of the denominator and turn our denominator into a real number. So again, really, really, really fancy equations. Are they worth memorizing? Absolutely not. All right, just understand that if we want to divide by a complex number, we do so by multiplying the top and the bottom by the complex conjugate of our denominator. So in this particular case, I would take 5 divided by 1 plus I, and I would multiply the numerator and the denominator by the complex conjugate of the denominator. All that means is I change the sign in between my real parts and my imaginary parts. Why am I allowed to perform this operation? Well, it's the exact same thing as multiplying by 1. Now we can multiply fractions as we normally would. Numerators times numerators, denominators times denominators. This gives us in the numerator 5 minus 5i. Notice that when we use the distributive property of multiplication in the denominator, 1 times 1, my first term gives me 1. The product of my outside terms and my inside terms, that's a negative I and a positive I, those add to 0. And I have a plus I times a negative I, which gives me a minus I squared. Remember that subtracting I squared is the same thing as subtracting negative 1, which becomes addition of 1. I have 5 minus 5i divided by 2. Now, I would accept this as a final answer, all right? However, if it is possible to reduce either of the fractions, you must use the distributive property of division to reduce the fractions. In this case, it's not completely necessary, but you certainly could split this up into two separate fractions, 5 halves minus 5 halves I. Notice in this case, none of the fractions reduce. That is why it's not necessary to split them up. However, if you can reduce any of the fractions, you must split them up. Always a safe bet to split up your real part and your imaginary part. All right, let's try another one. 6 minus 7i divided by 1 minus 2i. Again, whenever you are dividing by a complex number, multiply by the complex conjugate. In other words, we need to change the sign in between our 1 and our 2i, right? Essentially, our goal is to rationalize our denominator. So I'm going to multiply the top and the bottom by 1 plus 2i. Again, multiply the numerator and the denominator by the complex conjugate of the denominator. All right, so now we can FOIL. In the numerator, 6 times 1 gives me 6. plus 12i minus 7i. Negative 7i times a positive 2i gives me minus 14i squared. And in the denominator, a 1 times 1 gives me 1. Notice that the products of the outside terms and the inside terms should add to 0. That should always be true. Again, when you're multiplying complex conjugates, you have to get a real number. So I'm left with 1 minus 4i squared in my denominator. Now we can begin to simplify. All right, I've got a 12i minus a 7i. That gives me 5i. I've got a minus 14i squared. I squared is negative 1, so this minus 14 times negative 1 becomes a plus 14. 6 plus 14 is 20, so I have 20 plus 5i on the top. Minus 4i squared in the bottom. This becomes a plus 4, which gives me 5 in my denominator. 20 plus 5i divided by 5. And now we can use the distributive property of division to divide each term in the numerator by 5, leaving us with 4 plus I for our final answer. In this case, you would absolutely have to divide both terms in the numerator by 5 because both of those fractions simplify. Again, simplify fractions wherever possible. All right, there you have it. Addition, subtraction, multiplication, and division with complex numbers. We got another example problem coming up, and then we'll talk about using the quadratic formula with imaginary numbers.